Hey folks, today we're going to explore the wonderful world of cubics. So these are the notes that you should already have. If not, pause the video and get them quickly jotted down. Not going to talk through them in any detail here. We will do so when we look at the examples. We're going to run through like 8 examples here of varying difficulties, and we're going to introduce a few different methods. Make sure that you are copying stuff down as we go through. Don't just like assume it will go into your head. Cheers. So we're going to use today to go through a couple of different methods for solving cubics. I'm going to start off with my own personal favorite, which is the grid method. This is a method of polynomial division. Essentially, it means it lets you divide algebra by algebra quite efficiently, which is the reason I like it. But look, we're going to run through it with a couple of examples here, and you see what you feel about it. So first thing we've got -1 is a root of this cubic, and we need to find the other roots. So if -1 is a root, then that means that z plus 1 is a factor. Don't forget that when you solve things like quadratics and you factorize them, you like reverse the sign. So if we're being told -1 is a root, that means z plus 1 is a factor. Okay. Second thing we do is we set up our grid. There it is. And we write that factor that we just found on the top there. So we've got z and we've got +1, and we're going to split that down the middle. So every power, don't forget to do that. Now, what happens next is we take whatever the largest power of the polynomial is. So in this case it's z cubed, and we're going to stick that in the top left hand corner of the method. Okay? And we're going to think to ourselves, maybe writing in a times sign here, if I had z and I wanted to multiply it by something to get z cubed, what would I multiply it by? And the answer would be, well, I would multiply it by z squared. So I'll stick z squared over here. And that kind of makes sense as a grid, so z squared times z gives me that z cubed. And more specifically, z squared times 1 would give me that the number over here has to be z squared. Okay, so now what? Well, now we look at the actual question, okay? So we've done our z cubes. We actually want to get minus z squared at the end of all this, and we've currently got positive z squared. So we're going to look on this little diagonal here, and we're going to say, well, we've got z squared, but we want minus z squared. So what would we have to do with z squared? We'd have to take 2z squared away from it. And then that diagonal would add up to the amount in the actual polynomial. Okay, and then we do the same thing we did before. What would this need to be for z times something to give me minus 2z squared? Well, it would need to be minus 2z. And then what would this be over here on the right hand side? This would be minus 2z because we're timesing it by 1. And then we repeat the process. And this is essentially what the grid method is. It's filling in a row and then working out what will make that row work. So what's the next thing we're going to look at? We're going to look at the z's. What's the color I haven't used yet? Orange. So we have 3 z's. Okay, and this diagonal here needs to add up to 3z. But it doesn't. It adds up to minus 2z. So we need to add 5 more z's. Okay, what would make that happen? Well, that would happen if this was a 5 here. And if that was a 5 here, then this would be a plus 5 here. And then we just need to do one last check. If we've done this right, then this number at the end, this plus 5, should be the same as what we've got here, because we don't need to do any more rows after that. If you look at like the powers here, we've got z squared, minus 2z, 5, they're decreasing all the way, and the same is true if we're going across this way. And we can't really keep decreasing after 5, we can't go to z to the minus 1. Because that is plus 5 and that was plus 5, we're actually sorted, and so we have divided the cubic. So what we can say is that this is the same as z plus 1, and then look down the left hand side of our equation, times z squared minus 2z plus 5. Okay, well, Why have we done that? Well, it means we can now properly find the other roots by solving this quadratic that we're left over with. So we obviously know that z equals -1 is a solution because we were told that right at the start. And for the other ones, we can stick it into the quadratic formula. We can say we've got z is 2 plus or minus the square root of, let's see, what's b squared? 4 minus 4ac, so 4 times 1 times 5, all over 2, and that will give me 2 plus or minus the square root of minus 16 over 2, which will be 2 plus or minus 4i over 2, which will be 1 plus or minus 2i. And there's our complex conjugate pair of roots. So there's all of our solutions. Okay, so that was a bit of a long-winded example, but I think we need to properly explain how that works. I'm going to try it a couple more times now. So, similar sort of question, but it does have actually a slightly different open. It wants us to show 2 as a root in the first place. Now, how do we actually do that? We sub in 2 and we show that we get 0 out here. So that would be 2 cubed minus 6 times 2 squared plus 21 times 2 minus 26. That'll be 8 minus 24 plus 42 minus 26. And yeah, that equals 0. That would be enough. A show that question is very specific in maths. It is not enough to just say f2 equals 0. You do have to actually show the calculation. And we would have to say at the end, therefore, I suppose z minus 2 is a factor because that's what that's trying to get us to show. But we have shown 2 as a root. So it says we've got to find the other 2 roots here. Because it's cubics, there will be 2 other roots. So let's set up our grid again. Remember that you're going to put z and minus 2 across the top. And then we're probably going to have 3 things down the side. And what's our first thing? Our first thing is going to be the fact that we have z cubed as our leading power. And so that tells us this is going to be z squared. Now if you want to have a go at this, pause the video first, see what you come up with, and then see if it matches up to me. I'm probably going to talk through this a little bit quicker now because it's the second time we've seen it. I'm going to start that explanation in 3, 2, 1. Okay, so we're going to have minus 2z squared here from multiplying z squared and minus 2. But we want to get to minus 6z squared, so we're going to have another minus 4z squared to make that happen. That means the number here has to be minus 4z. That means the number here has to be plus 8z, minus 4 times minus 2. But we want 21z, so this is going to have to be 13z that we add to that to make that happen, which means this is going to be 13. Let's put that in green. And it means that the number left over is minus 26. That is the same as what we had in the equation, so we know we did it right. And there we go, we can get that our factorization therefore is z minus 2 times z squared minus 4z plus 13. So I like this obviously because it's fast. You get your solution out quickly, it doesn't take up a lot of room, and it scales up. So your method of like comparing coefficients is probably quite good for cubics and will work in comparable time. But we're going to look at quartics soon, and this is far, far quicker than trying to work out a quartic in your head. Anyway, so we need to get our solution. So z equals 2 is obviously one of the solutions, and the other one is going to be quadratic formula. So 4 plus or minus the square root of 16 minus 4 times 1 times 13 all over 2, so that will give me 4 plus or minus the square root, I think that's minus 36 all over 2, so z is 2 plus or minus, let's actually wait a step, 4 plus or minus 6i over 2, so our complex conjugate pair is 2 plus or minus 3i. There we go. So we solved that one in 3 minutes. Let's try and do this next one, I think it's the last example, even faster. Okay, so you're smart people. I'd like you to try and do this one yourself and unpause when you're ready to see. Okay, going to talk through it in 3, 2, 1, go. Okay, so we want to show 3 as a root. So we're going to do 2 times 3 cubed minus 4 times 3 squared minus 5 times 3 minus 3. That's going to give us 54 minus 36 minus 15 minus 3, they add up to 54. That equals 0. We have shown it is a root. What does that tell us? That tells us that z minus 3 is a factor. Okay, so I'll set up my grid. My grid looks something like this. I'm going to have z minus 3 along the top. And our first power is going to be 2z cubed, so that means we need to start with a 2z squared here, which means, oh, hang on, wrong place. That should be a 2z cubed, which means that this is going to be our 2z squared. Multiplying that out, that means we're going to have minus 6z squared here, but we want minus 4z squared, so we're going to have to add 2z squareds to that. For that to be true, that means this has to be 2z. And that means that this number over here is going to be minus 6z, but we want minus 5z, so we're going to need to add a z to that. This means this is plus 1, this means this is minus 3, and minus 3 is exactly what we should have, so we know we did it. So the factorization is therefore z minus 3 times 2z squared plus 2z plus 1, I suppose equals 0. And so our solutions are going to be z equals 3 and z equals, and then we'll do the quadratic formula. Don't forget to put 2 times 2 on the bottom. A lot of people just put 2 instinctively, myself included. So minus 2 plus or minus, that's the square root of minus 4 over 4, which is minus 2 plus or minus 2i over 4, which is minus a half plus or minus a half I. So there are our solutions. That took 2.5 minutes. You can see this is a very speedy way of getting stuff done. Okay, one more to look at here with why we might sometimes run into difficulties. Okay, so here we've got a different root. We've got we've got minus 4 plus I as being our roots. We're not being asked to verify anything, but there we go. And we want to find the other roots of this equation. Now, if that's a root, then that means that z plus 4 minus I is a factor of the equation. Then we need to change the signs if we're putting it into a bracket. But it's quite hard to divide by that. It's going to involve quite a lot of complex work. So this is where we want to use the other fact that factors come, if they're complex, come in conjugate pairs. And we can say that as well as minus 4 plus I being a root, then minus 4 minus I is a root. And so the other factor that could exist would be z plus 4 plus I. So from there, we could kind of know that this is going to be something like z plus 4 minus I times z plus 4 plus I, and then some other z thing that we'd have to try and work out. How would you actually solve that? Well, this is where we have to kind of multiply our things together. So we're going to ignore that z plus k for a bit. And we're just going to think about, well, what do we get if we multiply these two roots together? So we can do this with a grid if you want, and we'll point that out. So we have got z, 4, and I, z, 4, and minus I. And that will give us, don't have to do any working out now, z squared plus 4z plus iz, yikes, plus another 4z plus 16 plus 4i minus iz minus 4i and minus I squared, so that's going to be overall plus 1. Yeah, because minus 1, yeah. Now, luckily when you do this, loads of this stuff cancels out. So the minus iz and the plus iz cancel, The minus 4, well, that is a plus actually, so I should leave that as a plus. That does not cancel. The minus 4i and the plus 4i cancel out, and so that doesn't leave us with too much stuff. And we can see that overall that is z squared plus 8z plus 17. And then we can use the fact that, well, we have to times this by something, and that'll give us the actual equation that we started with. Now, at this point, you could compare coefficients and work out, I think, pretty straightforwardly that k is minus 4, because 17 times k has to give us this minus 68 up here. So I very strongly suspect it is minus 4, but let's keep using the grid method. We want to divide the entire cubic by a quadratic this time, so we're going to divide it by z squared add 8z add 17, and we're going to see if we can get that z minus 4 that we suspect we should get. So top power is obviously going to be z cubed, because that's what we start with, and then that'll mean this has to be z, and it will mean that the other bits inside the grid are 8z squared and 17z. And then we could look on the z squared column. We need to get overall plus 4z squared, so we need to have take away 4z squared. For that to happen, this needs to be minus 4, which is good. That's exactly what we're hoping. And then this should work out minus 32z minus 68, and yeah, those are exactly, because that'll add up to minus 15z, what we want to get. So we can say overall that we have z plus 4i, z plus 4 plus I, and z minus 4 as our factors. So our roots are minus 4 plus or minus I. Those were given to us by the question really, and 4. Okay. So you can see there's some difficulties with the grid method when the complex number gets involved, because you have to do some multiplying out, but it is still applicable and still can be used. We're also going to consider another way of doing things though, and that is that we can solve these things using essentially the root rules. And I think you've already gone through these in terms of writing them down but not actually used them, so we're going to actually use them. Okay, there are 3 different things we can use. If we've got roots alpha, beta and gamma, then these 3 rules apply. So what can we say? Well, we know that, let's say that alpha is minus 4 plus I, because we know that's one of the roots we've got, and we know that beta is minus 4 minus I, because we know it's going to be a complex conjugate root, and we know that gamma is, well, we don't know what gamma is. So these rules should be true. Okay, it should be true that if we do alpha plus beta plus gamma, we get minus b over a. So remember, we're talking about like a being the amount of z cubed and b being the amount of z squared and so on. So this should be equal to minus 4. Now, does that actually let us solve things? Well, hopefully, because if we sub this all in, we get minus 4 plus I, minus 4 minus I, and then plus whatever gamma is equal to minus 4. If we simplify the left-hand side there, that'll give us minus 8 plus gamma equals minus 4, because the i's will cancel out. And so gamma is just minus 4 plus 8. Gamma is just minus 4. That's our 3rd root. That really didn't take very long at all. So the grid method is really good if you need to divide through by a particularly a polynomial factor. But if you're just trying to find roots, this can be far, far quicker. Okay, let's look at the same questions again, and let's try and approach them with a roots method. Okie dokie, so this is the first question that we looked at. We had minus 1 being a root of this, and we want to find the other roots. So let's apply our rules. So we know, for starters, that alpha is minus 1, because we're told that in the question. Beta and gamma we don't know, so let's just call them a plus IB and a minus IB. Shall we? Yes, let's. So let's apply this here. So we've got alpha plus beta plus gamma is minus b over a. So putting that all together would give us alpha is minus 1 plus beta plus gamma, so it's going to give us just 2a because the IBs will cancel out. And then if we label up our cubic, minus b would be plus 1, and then a is just 1. So we've got minus 1 plus 2a equals essentially 1. If we add the 1 across, we'll get 2a is 2, and so a is 1. That's one of the things sorted. Cool. Now my suggestion to you would be, use the first equation and the last equation. The middle equation requires the most calculations, and I would only use it if I was essentially quite desperate. Anyway, so we've got alpha beta gamma is minus d over a. We now know that a is 1. So we can type this out as being, okay, minus 1, that's our alpha, times beta is 1 plus IB, times gamma, which is 1 minus IB, and all of that is equal to minus d over a, so that's equal to minus 5. What would you do with this? Well, we could expand that bracket and then times it by minus 1, and then we've got just an equation in B to solve. So that will give us overall 1 plus IB minus IB, and then minus I squared B squared. So minus I squared B squared, minus I squared will go to plus 1. So it's overall plus B squared at the end there. Then we need to think about things that cancel out. So IB and minus IB will obviously go away. And then we can expand it. So we've got minus 1, lots of 1 plus B squared is minus 5. And so that'll give us minus 1 minus b squared is minus 5, which will tell us, let's move that out of the way, b squared equals 4, and so b is, well, plus or minus 2. But we know we're doing plus or minus b anyway, so that shouldn't make a difference. So we get from that, putting our two bits of info together, that a is 1 and that b is 2, or well, plus or minus 2, that our roots are minus 1, 1 plus 2i, and 1 minus 2i. And very pleasingly, those are the exact same roots we got using the grid method. It'd be a terrible shame if you got different answers with different methods. Okie dokie, so let's just look at, again, a few more. Again, I'd like you to try these, I think, first, using a root method this time. You know the answers that you're trying to get. I think this one was 2 plus or minus 3i, but you can look back a couple of questions and see. We're going to use a root method. We'll use alpha, beta, and gamma, and we'll use alpha, beta, gamma as well. So I think these are the two that we need to try. Over to you. Unpause when you're ready. Okay, so I'm going to go through this quite quickly. We've got alpha is 2, and then we've got beta and gamma are the things that they are. So put that into the first equation, we'll get 2. Should label up my diagram, I suppose. Plus 2a, that's my beta plus gamma, is minus b over a. So it's minus 6 over 1, so that's equal to 6. So 2a is 4, so a is 2. So far so good. From the second equation, I would get alpha, beta, gamma. So I'll get 2 times 2 plus IB, 2 minus IB is equal to minus d over a, so it's equal to 26. So I could actually be sneaky and divide through by the 2, so I think I will do. And that just leaves me with the bracket to expand. That'll give me 4, and we know the middle terms will cancel out, so we may as well just go to straight saying 4 plus b squared at this stage. So b squared is 9, so b is plus or minus 3, and that'll give me that my roots are, as expected, 2, 2 plus 3i, and 2 minus 3i, just putting those two facts together. Cool. Okay, let's try, I think there's one more. So again, I'd like you to try this first, and then unpause when you're ready. Okay, let's go. So, first method. That's a terrible square. First method. There we go. We know that 3 plus 2a, that's going to be my alpha plus beta, is equal to, what have we got here? We've got beta, b is minus 4, so that's going to be plus 4 over 2, so it's going to be equal to 2. 2a is equal to minus 1, and a is therefore equal to minus a half. Then we can go to the second one. So alpha, which is minus a half, times, which is 3, times beta times gamma, so that's minus a half plus IB minus a half minus IB and that's all equal to minus d over a, so it's equal to 3 over 2. Cool, okay. So let's do the same thing we did before and divide across by the 3. That'll mean we're equal to a half. And then let's expand our bracket, and we know that the middle bits will cancel out, so it's going to be minus a half times minus a half, which is a quarter. And IB times minus IB, which will be plus B squared, is equal to a half. So that tells you that B squared is a quarter as well, and that B is plus or minus a half. Put those two facts together, and we get our roots as being 3, minus a half, plus a half I, and minus a half I. And you can see there that there's real shortcuts and speed ups once you know what you're doing. Okay, cool. So what we essentially did there was the first few questions of exercise 1F. Obviously we did them in 2 different ways, which makes it lovely and special, but there we go. What I'd like you to try is the same exercise, questions 5 to 8, using any method. Obviously we need to understand all of these, but part of the key is obviously going to be choosing the right method for the right job. Questions and answers will be attached to the Teams post. Best of luck.